Hi everyone, welcome to the lecture on neural networks as part of the machine learning lecture series by egate.ai. I am Dr. Amrith Krishna, your lecturer for the series. So today for this lecture we will look into neural networks. So we have seen linear threshold units or linear classifiers. We have been seeing quite a few of them, including the perceptron, the logistic regression and others. Here is the illustration of such a unit for a 4-dimensional input. So you can see the illustration here, just like in perceptron. We have an input with 4 features, which is x1 to x4 the features. So naturally we should have, which we represent by x typically. We have a weight vector which has weights again of 4 dimensions, right? So which belongs to the weight vector w. We have a bias. So we take the dot product, sum it up with the bias, and then take a threshold, which was the sign symbol. And you can see this formulation here. So we have different algorithms like perceptron, logistic regression, which can be used to learn this. So the dot product of weight vector and input and the sum with bias leads to the final output, which is then thresholded to predict a +1 or -1. I hope you remember this. And we can completely write the same mathematically as shown here. Now, what we haven't addressed here is that where do these input features come from? So I'm talking about x1 to x4. Where do these come from? Further, what if these x's here are not actually the features we designed, because there is a feature selection or a feature space design that the humans have to do or generally used to do. So what if these are not actually those features that are designed, but instead they are just raw observations from another classifier? What if these features x1 to x4 were themselves produced by another classifier? So the idea is really cool. The question is that can we really do that? So let's say we have a classifier or a final classifier with a weight vector w, and you can see its weights being w1 to w4. And this is for the final classifier. But it is not taking in the inputs xi's directly, right? So there is x1 to x4, but it's not taking it directly. Instead, what if all these inputs create a new classifier whose output is the feature to the final classifier? So if you see here, there is x1 to x4, there is a 1 for the bias. I am doing this dot product and summing the bias. I am having the thresholding, and this unit then forms the feature for w1, which is one of the elements of the weight vector w, right? So if we can construct multiple such instances, right? So I have suppose w1 to w4 is my weight vector, which means I have the final classifier is expecting 4 features, and each such feature is obtained from a different classifier. So every feature that the final classifier uses is itself computed by a different linear classifier. So what we have invented here is a 2-layer feed-forward neural network. So you may see 3 things termed as layer, but I am calling it a 2-layer feed-forward neural network. So I will explain why is it so. So there are 2 layers of predictors. So whenever you see this summation and thresholding, which may be a different operation, but for the time being, whenever you see the combination of summation followed by thresholding, then those layers are predictor layers, and there are only 2 layers of that. There is a hidden layer and an output layer. The hidden layer is producing a good feature representation, and the final layer can take care of the classification or the separation. So each dot product followed by, in this case, a threshold is called a neuron. So each dot product here, which is shown by the symbol sigma, and then it is followed by a thresholding, which is a sign symbol. So this is what we call as a neuron. So more generally, a dot product followed by some non-linearity is a neuron. It need not always be a thresholding. So in this diagram, there are 5 neurons. So can we mark them and see if we got those correct? So I would say this is one neuron, this is another neuron, this is another neuron, this is another neuron, and then there is one neuron here. So there is 4 in the hidden layer. So this is the hidden layer, right? We have marked it here. So this is the hidden layer, and 1 in the final layer or the output layer. So there are 5 such. But where do the inputs or the features really come from? So we have a 2-layer neural network, and we can see that the features are added at the input layer, and you have a hidden layer and a predictor. But is the input layer, the features that you see in the input layer, do they really come from a hand designed one? Or whether they may come from another neural network in itself, and that leads to a 3-layer neural network. Similarly, we can keep on asking this question and extending the number of layers. So let us try to formalize this notion. So neural networks are a robust approach for approximating real valued, discrete valued, or vector valued functions. As of now, they are among the most effective general purpose supervised learning methods currently known. Please don't confuse it with the AGI or artificial general intelligence. What I'm trying to say here is that they can be used for a diverse set of specific tasks, but we still have to train each of them for the specific task. They are a family of functions or a hypothesis class. They seem to really good for complex and hard to interpret data, such as real world sensory data, video, speech, text, etc. So it can be, what you see today, right, in ChatGPT, a lot of them can be attributed to pretty much like some of the basic fundamentals. Some of the fundamentals can be attributed to what we see in this slide. It is an algorithm that computes the gradients in the algorithmic way. It enables gradient-based learning of neural networks and has been shown successful in many practical domains. So I assume you have heard of neurons, both biological and artificial ones. So biological neurons are core components of the brain, and the nervous system consists of dendrites that collect information from other neurons, an axiom that generates outgoing spikes. Now, what you have to keep in mind is that modern artificial neurons are loosely inspired by biological neurons, and the emphasis is that it's both loosely and it's just inspired. There are many fundamental differences. So don't take the similarity seriously. A neuron accepts a collection of inputs, say a vector, and produces an output by applying a dot product with weights W and adding a bias term B, applying possibly a nonlinear transformation called an activation. So there's an activation, dot product, and summation with the bias term. Now, other activations are also possible. So the activation shown in the previous illustration was a threshold one, threshold activation, which you can see here. Another activation is a simple dot product, which is called as the linear unit. So basically no change to the input. It may very well be a sigmoid, which is an activation that is applies to the which simply applies the sigmoid function, and it's very similar. Like, so we have seen this in logistic regression. Then there are others like TANH or ReLU, which is rectified linear unit, and a lot more exist. So we have defined a neuron and given a neuron. Now we can define a neural network. So a neural network is a directed acyclic graph. And this neural network is a function that converts inputs to outputs, and it is defined by a directed acyclic graphs. The nodes are organized in layers which correspond to neurons. The edges carry output of one neuron to another associated with weights. So to define a neural network, we need to define three things. We need to define the structure, that is what the graph is. For each node, define what the activation function is. And we need to define the edge weights. So here, the structure and the activation functions are predefined part of the design of the classifier, and hence we call them the architecture. The edge weights, also called as parameters, are learned. So these parameters define the functional behavior of the network. Functional behavior of the network, which is learned from the data. The only job of learning is typically to weight the learns where the structure and activation functions are predefined. So the number of layers, number of units, number of nodes, etc. are basically forming the structure of the graph, or it basically tells how many nodes, how many of them has to be connected, whether I should drop a connection between two, etc. The final activation function. These two are predefined by someone or a team, and the only thing that is learned using a machine learning algorithm generally is this edge weights or the parameters. So we may have the same architecture, but depending on the data, different edge weights may be learned, and depending on the task, the data may vary, and that means that the functional behavior may vary, even if two neural networks have the same architecture. So they may produce outputs for even completely different solutions or different tasks. Now, what functions do neural networks express? Imagine that you encountered a single neuron, a neuron with a threshold activation. It is nothing but a linear classifier. Now, if we have two predictor layers, two layers with threshold activations, you can draw convex polygons in the feature space. So everything inside the polygon is a positive and the rest is a negative. So now the expressiveness increases when we have two layers or a hidden layer followed by a predictor layer. Now, if we have three layers, we can draw unions of convex polygons as shown here. So in general, neural networks are universal function approximators. Any continuous function can be approximated to arbitrary accuracy using one hidden layer of sigmoid units. Approximation error is insensitive to the choice of activation functions. Two-layer threshold networks can express any Boolean function. So that covers our neural network section. This is probably the shortest lecture in the classifier series. Thanks everyone. Now we will see SVM in the next lecture. Thank you.